Assalamualaikum. So today I'm going to discuss about this tutorial, kinetics of corrosion. So in this tutorial there are 5 questions. So let's solve the question. So question 1. Okay, look at this question. Calculate the corrosion rate in millimeter per year. Okay, what is the material? Iron. Okay, immersed in seawater, so produces current of, this is the value of current produced because it's spontaneous reaction. So the atomic weight of ferrum is given, as well as its density also given. So first you must know the formula to be used. This is the formula in order to get to express the corrosion rate in millimeter per year. This is the constant. Alright, so after that you must know how to convert this current density. So given in ampere per meter square. So in order to use this equation, so you must current density must be in this microampere per cm square. So from this ampere per meter square, you must convert to microampere per cm square. So after that, so you add insert this value current density into this equation, and the answer is 0.58 millimeter per year. Next, so this time the metal is zinc. Okay, experience corrosion in acid solution. Okay, according to the reaction. So the overall reaction is given. So zinc will dissolve to zinc 2+, and the cathodic reaction is hydrogen evolution. Okay, the rate of both oxidation and reduction reaction are controlled by activation. Okay, the process of corrosion is controlled by activation polarization. So both have slope. Alright, so there is no concentration polarization. So these are the parameters polarization data, okay, given for this activation polarization. For metal, the top value and the bottom value is the cathodic reaction. Okay, so what you need to do is to calculate, okay, the corrosion current density, I core, as well as corrosion potential. So in order, let's say you have this, if you have to plot even diagram, so this is voltage, this is I, so this is the E equilibrium for metal, zinc. So this is E equilibrium for cathodic reaction, hydrogen plus to hydrogen 2, and also each reaction has its own exchange current density. Okay, for zinc, the exchange is 10 power of negative 8. Okay, so then for hydrogen is more negative, 10 negative 10. Okay, so this is the cathodic I naught. So this is the anodic I naught. Okay, so they will reduce and this one will oxidize. So you need to calculate to the I core as well as E core of this reaction, zinc. Okay, so this is beta A. So this is beta C. Okay, so you must have 2 reaction. Okay, at the end you must have 2 equation. Equation 1, you focus on anodic reaction, this side. Okay, this side. Alright, so you must use the anodic process. Okay, the over potential of A, anodic process. So this equation is this one. New over potential is equals to E core, where the new E deduct with E equivalent, where does it start from? Okay, equals to beta A for anodic process, log I core, where it stop. Okay, then where does it start from? This I naught is the starting point, exchange current density. Okay, so you just add what value you can get from this question, okay, given. So if this is not given, so you just get it from the standard reduction potential from the table. Okay, electromotive force series. So this is unknown, this also is unknown at the moment. So this given, this also given, beta A also given 0.10. So you can derive one equation 1 for anodic process. Next, for the second reaction, you will derive equation 2. So you must use all data regarding the top plot here, this one. Okay, now you involve beta C and the hydrogen process. So hydrogen process is here. This is the equilibrium potential. This is the current density, exchange current density, and this is the beta C, the slope. Okay, you don't this one you must remember to add negative sign for this equation. So this is over potential. What is the formula for over potential? This is the formula. Eco divided with the, where does it start from? Okay, equation equilibrium for hydrogen. So this is beta C, negative sign must be included. Okay, log Ico, this is the point where you're going to stop. So this is where the starting point, I naught. Okay, so this is the value for hydrogen evolution. You can get it from the table or in the question also given. So then this is the slope, negative. Don't forget to put negative as well as this. Okay, so if divide, so if you want to expand it, so you should put negative and negative here. So at the end it will come up with this second equation. Okay, so now you have two equation 1 and equation 2. You just substitute either equation 1 to 2 or equation 2 into 1. So at the end you will solve eco, the corrosion potential, and also the corrosion current density. So please check again. So the value of eco must be in between these two potential. Okay, it shouldn't be above or less than this value. Okay, it shouldn't be more negative than this or more positive than 0. It must be in between. Okay, negative 0.38 the value. So if you get more positive, it means something wrong with your calculation, or more negative here, if your answer is negative 0.96, so that is something wrong, because the lowest is negative 0.76. Okay, as well also with this Ico. Okay, so Ico value should be more positive than the I naught for both. I naught is for zinc is 10 power negative 8, and for hydrogen 10 power negative 10. Okay, so your Ico must be positive, more positive than these two values. Okay, it shouldn't be more negative. Yeah. Okay, so 10 power of negative 4.2 is reasonable. Okay, then question 3. So question 3, so you need to estimate the diffusion layer thickness in centimeter for oxygen diffusion. Okay, so you, in this case, this is controlled by concentration polarization. Okay, this is IL. So the process is O2 plus 4 hydrogen and 4E equals to 2 water molecule. So in this case, N is 4. Okay, so this is IL. So diffusion coefficient is given here for oxygen. Okay, oxygen to diffuse to the surface. And okay, from this equation you must know how to write this, or you can check from the table. N is 4. Okay, F is constant. CB is given. CB here, this is in molar or mole per dm cube, but in this equation you must convert this to mole cm cube. Okay, remember that from dm cube you must convert to cm cube. Okay, so what IL is given. Okay, IL is given. Okay, this unit. What you want to know, you must know is this. Must get is the Nernst equation. Okay, the Nernst layer thickness. Nernst layer thickness. So this is the thickness. So you rearrange the equation Right, so this is D, this is N, F, this is C, and this is IL. Okay, at the end you can find the layer thickness, okay, in centimeter. Next, number 4. Okay, what is shown here is the polarization curve. What is the material? Iron. This is the area. What is the solution? Deaerated. There is no oxygen in that acidic solution. Okay, pH is 0. So A, write down the most likely anodic cathodic reaction for the above reaction. So you know what is the material? Iron. So iron is the anodic process. Will dissolve or corrode to ferrum 2 and release 2 electron. So what is the cathodic reaction? This is the condition. Deaerated. There is no oxygen, so you must use this. Hydrogen plus evolve to hydrogen gas. Okay, these are the anodic and cathodic reaction. B, determine the approximate values of E core and I core. Okay, so this is E, this is of potential, and this is I. Okay, so here is log I. So how to determine E core? You just look at this tip. Okay, very sharp tip here. So you just approximately determine here. So what I can measure is negative 0.224 corrosion potential. And to determine the I core corrosion current density, okay, you just take 2 points here at the linear or straight line here, and 2 points at the bottom here. So you just get a ruler and just do like this. Yeah, extrapolate this linear. Okay, you can find a cross. Yeah, at the cross, this is the value. Okay, probably I need to erase this, do it again, because initially I found it's negative 4.3. Okay, so somewhere here. Okay, so here negative 4.3, log negative 4.3. Not correct. Okay, you just do it and you should get this value. Okay, at this cross. Okay, here. So this is in log I. Log I is negative 4.3. If you anti-log it, you should get negative 10 power of negative 4.3. Okay, ampere cm square. Next, C. Assuming that the Tefel constant is 0.1 volt per decade. Okay, this is the slope. Tefel constant, beta. Okay, calculate the approximate value of exchange current density of the cathodic reaction. So you need to find E naught, okay, for cathodic reaction. So this is beta C. Okay, so you just this is the value. So use Tefel equation for cathodic. So use this. Okay, so this is given. Okay, so in this over potential has this the E core, because you just determine in B E core here from the graph, from the plot. This is the value at standard. You can get it from table. So beta C is given negative. Okay, remember that for cathodic reaction, beta C is negative value. So what you going to get from this equation is still missing is this. What is the exchange current density? Exchange current density for hydrogen evolution, the cathodic reaction. This one, 2 plus this. So what is I naught for that one? Okay, so I core you just determine from B here. Okay, so just put all the given information into the equation. So at the end you will find I naught for hydrogen. Okay, please check again the value. It should be logical. Okay, as compared to I core, it should be more negative than I core. Okay, so have a look at this. Okay, you have to find this is beta C. So this is beta A. Okay, this is I core. So I naught should be more here, more negative. So from your calculation is about here, negative 6.5. Okay, it is logical. Okay, so not somewhere here more positive. It's wrong for the I naught. I naught should be more negative than I core. Okay, and the final question, last question, question 5. Okay, iron, this is the material, corrodes in, this is the solution, acid solution to iron 2. Okay, iron will dissolve to ferrum 2 plus and release 2 electron. So exchange current density for the anodic oxidation is given 0.01, and this is alpha. Okay, so you must remember that beta is 2.3 RT, alpha and F, this is the symmetric coefficient given. Okay, so the standard electrode potential for ferrum, this one is standard is negative 0.44 volt, and this is R, this is T and F. Okay, you want to calculate beta. Okay, R is given constant and T is 298 Kelvin, F is constant, and N, you know, N is 2. Okay, so alpha is given, so you can get slope. Okay, for that anodic reaction. Yeah. Okay, so you can get beta A. Alright, so you must use this Tefel equation for anodic process, because this is anodic process of ferrum to ferrum 2. It's going upward. Okay, so this is I naught. So this is where does it stop? Okay, I core. Okay, I core. Beta is given. Okay, I naught is given. Okay, so I naught and I core. Beta you can calculate, so you can get over potential. So how far? This is negative 0.44. So this is over potential. Stop here. So this is new E. Okay, so this is E equilibrium for ferrum. So this is A. You want to calculate this over potential. So this is over potential, 0.1 volt. It means that it has moved from this point to this point. So this is the gap, the difference. Okay, the over potential is 0.1 volt. So for B, calculate the corrosion potential at the same current density. So for this equation, over potential, there is E core. Okay, so E core tidak E equilibrium for that metal. Okay, you know this, and you also know the over potential. You can get E core. Okay, so E core is negative 0.34. It means that ferrum reaction has moved. The anodic reaction has moved to negative 0.34 volt. This is new E. Okay, when you take this and deduct 0.44, the equilibrium, the starting potential, you will get this, the over potential. Okay, so thank you.